So on to non-metric multidimensional scaling, which we started last time by contrasting it with principal components analysis and trying to show how it attempts to alleviate some of the problems with using a method like principal components analysis that's assuming linear relationships among your variables. And I want to start today by doing a little example data set. And this is the data set that's actually in your textbook on that table 16.5. But what I'd like to do is get volunteers from class to represent each of the sample units. And we'll do a non-metric scaling ordination up front here. And the nice thing is we can do that without solving any equations. And it's very similar to the process that the computer is doing. So I need 5 people who aren't afraid to be a little bit foolish or whatever. You have to wear a hat. And I've got 5 hats, and they're different themes. Like, here's something like a bird nest made out of rope. You're into birds. We had another bird person here somewhere, too. So everybody's hiding. Well, okay, we got bird nest. We got a mussel. Somebody feeling oceanographic or intertidal. There's a lichen. A flower. Okay, so I need volunteers, 5 volunteers. 1, 2, 3, 4, and 5. Thank you. Okay, so each person coming up here is a sample unit, so you can grab an appropriate hat here. And what I've done then is calculate Sorensen distances from that data set I just showed you among each of these sample units. And each rope has 2 numbers on it. So this is the distance between 2 and 3. So your 2, maybe you can undo that and hand the other end to 3. Actually, don't hand the other end to anybody right away here. We gotta do something first. 4 to 5, and 1 to 4. Here's a 1 to 3. Is it? 3 to 5. 1 and 2. Oh, I haven't given you any yet. You're 5. So somebody, oh, there's one for you. Who's 3 to 4? Can you undo that one? Don't hand it to him yet, though. 2 to 4. You can do that one. Okay, so we've calculated all these distances, but the first step, as I mentioned last time, with non-metric scaling is to start with a random configuration. So if you guys would just take some random position up here. Now this is our ordination. We're doing a 2-dimensional ordination, and the axes are along this wall and then a perpendicular to that. So here's axis 1 and axis 2, or the names are arbitrary. It doesn't matter. So this is random, huh? Okay. Well, whatever. Now, everybody's hat staying on okay? Okay, let's see. Yeah, good. So now what we want to do is grab the other end of the rope. So we're going to connect everybody by the appropriate distances. So each person has a distance from every other person, right? And you can't move. Now, it's okay to take a step to grab the end of the rope, but you got to go back to where you were in your random configuration.
Oh, here's a 2.
Oh.
5. And that one again. This is stressful.
Yeah, this is stressful. That's the idea.
Got it, 5. I need a 5. The other one. Is that 1? There's 3. Oh, here's 1. Here's a 1. Oh, there you go. Here, I can shoot you.
Okay, is everybody connected?
Yeah.
Okay, so the object of this is that the ordination should reflect these distances, these point-to-point distances, right? So, and our measure of departure from fit is called stress. Now, a least stressful situation, everybody's rope would be about the same distance. There would be no big slack parts and no tight parts, no leaning over or anything like that. So, and actually these could be elastic ropes, and you could be saying, how much tension is on it. It should be all the same distance. So obviously our map here, our ordination, leaves something to be desired in that the distances between our points in the ordination space are not mapping very well onto the actual distance matrix that we're trying to fit to. Okay, so the way non-metric scaling does this is by evaluating your most stressful axis, like axis 1 and axis 2. You're going to take a step, in one step only, in the direction that will reduce stress for you. And every point is evaluated individually on this. So Michael here is going to evaluate, well, he's got some big slack here, so he'd be wanting to move away from 3. That one's kind of tight, so we'd be moving towards 4. So everybody can go ahead and take one step. You have to take a step.
And so an extra slack one is just as bad as an extra tight one?
Extra slack is just as bad as extra tight. Okay. So what do you think? Did they improve it at all? I think they did, actually. And so after each step, we will reevaluate what direction they need to step in to reduce stress. Yes?
So it seems like once one person took a step, that might change the other person's decision. So what order does that actually happen in?
It happens simultaneously. So each point evaluates the direction it's going to move. They move. But if they move in the sort of opposing directions, or let's say such that it increases the stress between them, presumably that will be fixed in the next step, or maybe partially fixed. So it's going to be a successive approximation, trial and error process. So go ahead and take another step. Okay, starting to look like a good ordination here.
I think we'll get back on the line axis.
Yeah, oh, really? Oh, now we've got one disconnected here. What's that one hanging down?
This is 30.
We're connected. You're just far.
Well, how can there be an end on the floor? Somebody's got to be holding the ends. Okay, that looks good. Okay, so let's take another step. Oh, man. Looks like, Johanna, you might need to do some climbing over the... Now, actually, we're doing a two-dimensional ordination. If we had some step ladders, we could do a three-dimensional ordination. And you can see that we would get better fit with a 3D configuration than a 2, because we're clearly not going to be able to solve this problem completely in 2 dimensions. So go ahead and take another step. Okay, well, I think the room is sort of constraining us here. But that's not bad. I mean, compared to what we started, wouldn't you say that we've reduced stress considerably? I see a couple fairly slack ones. But, like Johanna's got some slack ones coming over here, but what can she do? She's tied down over there. Now, if those were a little bit stretchy, we could do that a little differently. But okay, so this is our final configuration that these guys came up with, and this was from a random start, right? Now, if we're actually going to run this on the computer, we'll do 100 random starts, but I think that would take too long. But this is the migration of points for a single run on the computer that is similar to what these guys were doing. So the arrow shows the starting configuration, or starting position of each point, and then how it's migrating through axis 1 and 2. And here's how the stress changed over these iterations. And the computer did 20 iterations here. So I suspect they were taking a little smaller steps than the class was. And the stress actually bumped up quite a bit at one place, but then happily it rescued itself. So that could easily be that situation that somebody asked about with sort of moving at cross purposes to each other. So with the computer example, here's the final configuration, and let's compare that to what we've got here. So number 3 is out in left field here, or right field it is, as it is here. So we did pretty well with that. And then it looks like 4 and 1 are closest. Well, there's 4, 1's kind of back here, which this actually is not necessarily a better solution than what you've got here, but I'm guessing it probably is. And then 5 is back there. Now 1 and 2 here are in the same position. Well, you guys are close. So it's actually a reasonable approximation of what these guys were able to do here. So if you're going to do it in 1 dimension, then we could have everybody just line up at random positions along a line here, and then their movements would be constrained to along that line. So you can see that final one-dimensional solution is probably not going to be, the scores on that are not going to be the same as if you did it in 2 dimensions. Okay, thank you.